Greetings, friends. Today we're going to be looking at the double angle identities. Double angle identities are those magical identities which tell you what cos of 2 theta equals and what sine of 2 theta equals. The way we're going to work them out is we're going to look at rotations. Let's say here we are. Here's some point around the origin, and I rotate it by an angle of theta, and then rotate it by angle of theta again. So that's 2 rotations. That's the same as a single rotation by 2 theta. So what I'm going to do is I'm going to look at the rotation matrix for rotating by 2 theta, and I'm going to compare it by the composition of rotating by theta twice. So here's the angle for rotating by 2 theta. Let's write, I'm going to be a little bit lazy. That's how I write cos of 2 theta, c2 theta. Okay, that's the matrix which will rotate a point by 2 theta, and that's equal to rotating by theta once and then rotating by theta again. So that composition transformation is the product of the 2 individual transformations. There we have it. And let's take matrix multiplication here to find the matrix which represents that total transformation. So we have cos of theta times cos of theta. That's cos squared theta plus negative sine of theta times sine of theta. Okay, then cos of theta times sine of theta plus cos of theta times sine of theta. Okay, then we go cos theta times negative sine theta. And then we have negative sine theta times cos theta. Then we have negative sine times sine. And cos times cos. This also simplifies. So now we can do some comparison. In the reds, I'm going to look at cos theta. So here we have cos 2 theta here, and cos squared theta minus sine squared theta. And then again, we have cos 2 theta here. That equals this component, which again is the same. So when I see cos of 2 theta, that equals and then what have we got? Orange. Let's do orange. No, let's do blue. So then I look in the blue and I say here I have sine of 2 theta. That equals 2 cos theta times sine theta. Then here I have negative sine 2 theta, and that equals negative 2 cos theta sine theta. So I can say sine 2 theta equals 2 times cos theta times sine theta. Okay. Now, let me see if I can use these. What would make the double angle formulas really useful would be to change them into the form where I can say cos squared of theta equals something. Okay, that's kind of useful. Let's see if we can get rid of this sine squared theta. So we use Pythagoras' identity that cos squared theta plus sine squared theta equals 1. So I'm going to rearrange it and say sine squared theta equals 1 minus cos squared theta. Okay, now I'm going to substitute this information here for sine squared theta. Okay, then I'm going to add cos squared theta to both sides. So on the left hand side I have 2 times cos squared theta. Then just divide both sides by 2. And similarly, we can do the same sort of thing for sine squared theta. And now I'm going to write that cos squared theta would be 1 minus sine squared theta. So I'm going to substitute that in for cos squared theta. Okay, now add sine squared theta to both sides. And divide both sides by 2. So I've used the double angle formulas, identities, to get some other expressions. These other expressions are really useful for integrating. Now here's just a quick example. Okay, so let's say a question is asking me to find the integral of cos squared x, let's say x instead of theta. With respect to x, I can transform cos squared x into cos of 2x plus 1 over 2. Let's do it like that. Now, that's easier. The integral of cos is negative sine, and it's negative sine of 2x. Divide by 2, then we also have to divide by the derivative of 2x, because this is a u substitution problem in disguise. And then the integral of a half is x on 2. So this becomes, if you take out a factor of a half, it becomes that plus c. Always add c. So, I hope you had fun. That was just an example of finding double angles and rearranging to get some useful expressions and using them and all of that. So, Best of luck. Keep studying. I'll see you next time.